So, hello everyone. I'm Toon Verwaest.
I'm Camillo, Bruni.
And we are from the VA team. So we are specifically from the runtime subpart of the VA team. So we are the ones who are not focusing on GC, not focusing on the compiler, not focusing on the interpreter, not focusing on Blink.
So no fancy algorithms.
Yes. And we're going to talk about real-world performance, or how we moved from focusing on benchmarks to focusing on real-world web pages. So to give a bit of history, we used to be very much focused on benchmarks to get the VM running, obviously. And a very good place to start there was the SunSpider benchmark, which was already available, which was very, very tiny. And for getting just initial performance up, that's actually, that is a pretty good place to start. But pretty quickly, you run out of useful things in there. Right? This benchmark is just trying to measure the bitwise end operation, and that's not necessarily the most interesting operation for the real web. So because of that, we came up with our own benchmark, which was the V8 benchmark originally, which then in the end became the Octane benchmark, in which we put bigger applications. Originally, it started with benchmarks that we merged from other languages, moved over from other languages, and then later on we extended this with computationally heavy applications that we actually found on the web, like a PDF renderer, Box2D, which is like a library for doing 2D animations and so on. Which are useful applications, and the advantage for us was there that they were quite easy to move out from a browser setting into the V8 setting, because we are actually VM developers working on JavaScript. We are not so used to working within the browser, and it's also much easier to focus on just the JavaScript side if you can rip it out of the browser. And what we claimed when we came up with this benchmark is that so obviously they're complex, demanding web applications that users interact with daily will be improved automatically by also improving these benchmarks. If you actually profile one of these benchmarks initially, you will see that you're spending like 85% of the time in JavaScript. You're almost spending no time in C++, and this guides the way that we start optimizing for these benchmarks. So we obviously start looking at what are the JavaScript functions that we are executing, and what are the kind of patterns that we can see in there, and we start optimizing for those.
And yeah, so just to give an example how this might work, here this is this simple array push function. And so what this conceptually does is you just set the value at the length of the current array. And that's a very simple operation. But that's actually not what we do internally, because the JavaScript spec requires us to do this thing here. And we have almost side effects at any of these steps in between. And we're required to do these step by step. So you can imagine that this here doesn't quite match the expectations of a programmer when he sees array push. And to actually improve this and get it faster, what we first do, so the first step that is already tricky is actually to get to the push function itself. And internally, what we have is we create these hidden classes where we track the shape of each object. And that's a fast way to determine whether the array we get in here is actually still the original array. And if it's still the original array, that's if the array map is the unchanged one there, we actually can check if the prototype of that one, which is where the push function actually lives, is still the original one. If that's the case, we know, okay, it's the default push. And that's a very fast case. But you already see that this requires quite some machinery to get to that point. And we can use that in our optimizing compiler, that we actually do exactly these checks at compile time. So when we kept track of what arrays we get in, and we see, okay, it's actually the original one. The array prototype is still intact. When we've done that, that's the compile time pre-checks we do up there. We can actually do the fast operations down here. And you already see here that is already by itself quite tricky to do. It's not just simple as that. And by doing so, we can actually get a significant speed up. And in this case, I don't know, that's almost a factor 10 that you get out of that by actually making sure that you can optimize these fast cases. And that is impressive. You get on Octane, we got impressive speed ups quite quickly, because we had all these low-hanging fruits where the optimizing compiler could actually do really well, because we have a very limited set of input parameters. The data structures stay very stable. It's an easy target. You can go for it. You can optimize. You can go crazy. And next slide, I guess. What is also very important here with Octane, because it's running quite predictably, it's easy to run locally. We can compare against other browsers. And yeah, in this case, we're the green ones. We're better. We're faster. We're going up. It's just forward. It's massive. We're like full rush. Car analogy is here. Wind in the air. It's good. It's good times, right? But we don't see the wall coming.
So in 2010, there was already a group of researchers which asked this question, like, what if the benchmarks aren't actually representative of actual workloads? The problem then, of course, would be that compilers writers would be steered towards implementing optimizations that have little or no effect in the real world. So that brings us to the question, like, what is actually a good benchmark? There's multiple facets to a good benchmarks, and there's multiple perspectives that you can have when you look at the benchmarks. And obviously, a good benchmark needs to invariably be stable, reproducible. It has to come up with a single number. It has to, using a single number, tell you how fast something is compared to something else. But if you look at it from a VM developer point of view, you basically want to use a benchmark as something that gives you priorities for guiding your work, and it has to give you meaningful insights into how the language is actually being used by developers. So you want to use that to structure the object model internally to be able to speed up applications as they're used by users. Then there's the benchmarking facet to this. So you want to be able to compare different browsers, the performance of different browsers, and using a single number, that's really easy, right? Like if you see a single number, you can tell the number is higher, so this browser is obviously better at doing this kind of workload. It has to be cross-browser, obviously, and it should not be easily gameable because the number should stay meaningful somehow. For application developers, these benchmarks should actually contain patterns that you want to use, and it should also be cross-browser because you want all the different browsers to optimize for the kind of applications that you're writing. In the end, what users actually only care about is that any improvement on the benchmark directly reflects in their own experience, right? So if you go back to the SunSpider example.
Yeah, so coming back to SunSpider, this looks very harmless. Again, if you're assuming that JavaScript is a fairly static language. It actually starts already with the variable here, bitways and value. Somebody forgot to put the var statement in front of it. What it actually means is that's in the global scope. That's a normal property. That has to be written to the global object and read from the global object. That's not what you expect when you just look at it. A second thing is, and that, by the way, would also happen if we just declare that inside the function that just is leaked out to the global object. Second thing is the bitwise AND, besides the fact that the AND operation is not really useful in the web. I don't know, a use case where you would use that very frequently. But if you just look at it, ANDing a value that's pretty much soon going to 0, but next to that fact, we actually start at 0. So after the first loop iteration, we're basically at 0. So if you have a smart compiler, you just optimize it away immediately. You don't even have to do anything. But it's JavaScript, so you can have side effects. That's a global variable, so that can be changed in the meantime. Could be the ampersand, that is an operation that you could actually override potentially in some cases. And what you have to do here to actually make that fast, this is the last step here, since you have this tight loop here, actually to make sure that the optimizing compiler can kick in, we have to do on-stack replacement. And that's a really complex machinery, which means that you have the slow version of code running. At some point, we decide, okay, we actually have to optimize it. We have to go back, figure out the stack layout, swap it out, make sure we jump to the fast compiled version, map the old stack to the new one, and continue running. And that's quite a big machinery to just achieve this use case here. What we see as well is on the top and bottom, we have the timers. Seems innocent, but what if a GC happens in between? I mean, these benchmarks run fairly quickly, and we're talking about millisecond range. A GC is in the order of milliseconds by itself. So one GC in there, and your benchmark results are screwed. This is gone. So depending on how you look at it, this benchmark is highly flawed. It's very useful if you're working on optimizing compiler because you can actually really make sure that these cases that you hit in here go fast.
But if you're actually just looking at the number, obviously, then you can easily really very much go overboard and drive up the number in such a way that you look really, really good, but you're actually not positively benefiting anybody, right? So the guys who wrote the original paper that was questioning the value of benchmarks, they then actually came up with their own benchmark suite, which was JSBench. And they looked at it, so the benchmarks that they built came from this premise that we should look at the real world. So they, the way that they built their benchmark is that they actually scraped existing web pages like Amazon, Facebook, Google. So they basically hooked into the browser while it was running the page. They would basically figure out which snippets were running in there, write them out to a file, and then rerun them. And so they would record the snippets on multiple browsers, and then they would run the results on different browsers as well. And what they actually got out of this is a set of scripts that actually has a totally different profile than what you have if you just look at like the traditional benchmarks like Kraken, Octane, SunSpider, the ones that are on the right. So as I said before, like the ones on the right actually spend all of their time in JavaScript, but the ones on the left spend actually most of their time in C++. Based on these results, there was then later on a group that tried to optimize for this particular case. And they changed V8 and they threw out all the hidden classes, they threw out all the optimization that we had, they threw out the optimizing compiler, and they noticed that they could actually get 30% faster on this particular benchmark than V8 was without any of the optimizations that we had. Of course, by doing that, they also kind of threw out the baby with the bathwater, like on the things that were in Octane, which are not entirely unreasonable either. Like a PDF renderer, for example, is a useful application in itself too. You actually want to support this kind of use cases as well. There they actually got 5 times slower. So they traded 36% speed up for like an 8.5 times slowdown. And another data point where JSBench, which actually shows that JSBench itself is not entirely the best benchmark itself yet either, because it has to mock out a lot of things, of course. It doesn't run on a DOM. You can actually optimize across the DOM boundary, for example. But another data point that we had is that we later on saw a regression in this benchmark. Maybe you can talk about that.
Yeah, so it's hard to guess, but that just appeared at some point, and that's was that 40% regression. And typically you would attribute it to something, in the compiler, something advanced that went wrong. But if you actually look, so Toon changed something that is very practical on the user level, is that if you try to call undefined as a function, you actually try to infer where that came from. And in the fast path, the error message you would get is undefined is not a function, which is far from useful because that can be anything. And they actually figured out by going back, mapping back to the AST and figuring out where we are, we can actually print a much more detailed error message that actually guides you towards the error. And that's what we have on the right. And the fact that this gives you a 20% slowdown means that there's something seriously flawed in the benchmark. And actually what happened is that since they had to modify the runtimes to actually trace the websites, they inadvertently introduced errors. And what their approach was is typically that when they got an error, they assumed that the trace they got is invalid and they would discard it. But many modern websites, they actually have telemetry code on top level that whenever they get a JavaScript error, they would serialize that error, send it back to the server for an analysis because something might have gone wrong client side and you want to keep track of that. So what they actually wrote essentially benchmark for is error handling, because by introducing the errors, the websites were constantly throwing errors. They bubble up, they get caught by the machinery that actually serializes and sends it back to the server. And we uncovered that by changing something that is just related to actually rendering error messages.
When Speedometer came out, initially we had really bad performance on that as well. And when we profiled this, we actually saw that the profile was actually pretty close to JSBench, much more close to JSBench than it was to.
Just to quickly, are you familiar with Speedometer? What that is? Yeah, there's one guy. Okay, just to quickly explain. So Speedometer basically takes to do MVC application, implementing in different words coming to my head. Frameworks, thank you, that one. Doesn't even exist in German, so no excuse. In different frameworks, and they made a benchmark out of that. So it's running a website and just instruments the website to like enter to-dos and delete them. So it's using the full browser.
So it is actually running real frameworks, so real applications. It's actually running them in the browser, mixed in with the DOM, which seems much better to get this entire picture out. And so that gave us a new insight into how JavaScript actually works in the browser. So from our perspective, that was like we actually see a totally different profile. If you look at the same profile, that's what we get for Octane. Previously, you actually see that here you spent 74% of time in C++, and only like 20% of the time in JavaScript. And if you look at the actual profile, it looks really flat, so it's much harder to figure out what's going on than it was in the Octane-like benchmarks. So we started looking into ways of trying to understand what this application was doing, and we started playing with flags that we have internally. Like the first thing that we did was like tracing ICs, so the inline caches that we talked about before, figuring out how are they actually behaving here. Because in Octane, for example, you would most of the time stay in the monomorphic state or go polymorphic, but these applications are so small that most of the time they're much more contained and much easier to optimize. Within Speedometer, we saw much different patterns. We saw ICs that were constantly rewriting.
So to analyze actually this output, which is just serialized to the standard out, that's not really useful, really little tool, where you can actually dive down. So what you see here on the left is actually the types of for instance, IC misses we get. The first one is a megamorphic one. That means we got on wall call side, we got many different types in, and we basically don't know what to do anymore, and we cannot use the fast paths anymore. And on the right side, what you see is that you can actually drill down to specific locations. And in many cases, we can actually pinpoint a couple of locations in the sources where the majority of the IC misses happen. And that's something that's very easily detectable with that tool, which is a thin layer on top of the trace you saw before. And an additional system we have is we have our hidden classes, which track the shapes of the objects we get. And for benchmarks like Octane, objects don't change much. We have a very limited number of different objects and shapes we see. So this system is working really well. But in the wild, crazy stuff happens. And you get actually pictures like this. And that is sort of, I think that's a real stress test for graphics. It took a couple of hours to actually render that picture. But you can see how this actually differs massively from Octane, just looking at these distilled data.
But so using these small tools, we actually found some initial bugs. I mean, that always happens when a new benchmark comes out, especially if it's from a different vendor. In this case, it was an Apple benchmark, which is good. We can actually find bugs in our system through this mechanism. And we initially got really big speedups, but as you can see at the end, like it flattened off very quickly there. So we started looking at other ways of looking into the data. And we went back to like this graph that the JSBench guys had, where you see the different bars. We tried to recreate something like that, and that's especially an interesting data point because we can basically bucket up time spent in C++, and especially the boundary between JavaScript and C++ is an expensive boundary. So if you know why you're going into C++, that can actually help you understand where your time is going. We then later on actually we redrew the graphs that they had, although we do get slightly different results than what they were seeing. But you can see like that the Octane actually does indeed spend so much time in JavaScript, and Speedometer is, like JSBench, much less time in JavaScript. They don't actually spend as much time in ICs as they saw on JSBench, so the ICs are like these blue bars here. But still, you can see we're spending much more time in C++ and in many different components, and JavaScript is actually a very, very small part of it. Yeah, sorry. Wrong direction. But once we had this, we were actually curious how would this actually be in the real world. So we ran the same tool on real world web pages, and what we saw is that you get profiles that are much more close to Speedometer. This is startup, so that's obviously a specific workload that is less likely to even hit the Octane case, because you will still have applications that will do like expensive rendering or whatever. They might actually hit the Octane case, but startup especially, which is something that we are also traditionally not that great at, are much closer to Speedometer. I mean, once we did that, there was actually not much point anymore into looking into Speedometer and Octane. We just started looking into where is time spent in the runtime, given that we work on the runtime within the real world web pages actually. And so we bucketed it up as the runtime time. You see, like it's actually most of the time between 30 and above 50% of the time just spent in the runtime. Where previously we would, as the runtime, just service JavaScript and try to make JavaScript faster. And now we actually have to focus on just optimizing the runtime part as well. So then for the runtime part, we basically just split it up in multiple different buckets, and we got a really long tail of like things going on. Obviously, real-world web pages are more complicated than benchmarks, so you very often end up with like really small percentage of things that you can work on. But we use this to get a prioritization of things that we can work on, and so we ended up with a list of build-ins that are pretty important to the web according to what we can actually measure on the web, and we actually have had previously also bug reports for some of these things. But in many cases, we optimize them in the way that we optimize for Octane, right? So in the slow path, we just made it work in such a way that we could easily, in the fast path, get fast code, like the push case that Camillo showed you before. In the slow path, if we just track the right things in the fast path, we can immediately turn it into what we want. But unfortunately, we're not even hitting that, it seems. And so the way that we then started thinking about this problem instead was, if we're not actually hitting the fast path, let's try to make the slow path faster. So we started changing the way that these things were implemented. Originally, we implemented many of these build-ins in JavaScript. Originally, that was thought of as a performance thing by itself, because you could actually track feedback just like we would do for regular JavaScript code and then optimize it later. But this actually has a negative side effect too, that you have this overhead as well. For things that we control, we have the same overhead as what a regular application has to get good performance. And we actually know what we want, we know what kind of encodings we have, so we can specialize these implementations towards it. So the first thing that we did was just move it out to C++. You can even see here, this JavaScript function actually it was even already calling C++ with the percentage hasn't property there. So we just moved it there. And then we optimized that path entirely, so did the opposite as what we did with Octane. Rather than just moving it to the fast path, we just optimized the slow path first, tried to get some benefit out of that. And then we put in a code step before, which is essentially manually written assembler code, but we use intermediate representation of the optimizing compiler to write them, because we have so many different backends that we have to target. And that in the end gives you like a 1.8x improvement on just hasn't property.
So to come back to the array push example, this is what I showed you before. That would be the Octane case. We get one array type in, the array prototype chain stays intact. That's the original one. That's a fairly easy case to optimize. We know almost statically compile them what happens. And just to give you an example, if I would implement this push, an easy way would be to implement it the way it's over there. And actually in the wild, we see a couple of places that we have JavaScript built-ins that have been implemented in the library as factory functions. And go to the next slide. There are a couple of problematic cases. So that's what I showed you already before. Each of these dots is where we actually have to do a lookup. So here I have to look up the push function, which can be anything in JavaScript. JavaScript, you can go and monkey patch everything out. You can replace it. And that has been a strategy for some while to actually get chimps in and making functionality across browsers work the same way. But what this means, we have to make sure, that's what I showed you in the previous slide, that is exact the push function we want. And if I implement it, let's just go one slide back again, thanks. If I implement it myself on the right side, you see actually we have two of these places. And one is actually for assigning the property and one is for getting the length. So we have two places where things can go wrong in terms of what types and what arrays I get in. And just now the next slide, if just give you a quick overview, these 7 examples here, they all generate different internal array kinds. So first one is an array which has only integers in it, the second one with doubles, the third one with just normal objects. And then you have the corresponding ones which actually have holes in it. And the last one is a large array, which represent sparse array, which we internally represent as a dictionary. And from the user point of view, these things are all an array. There's no difference. But actually, from how we track the information behind, this is very different. This is all a different kind of object, different kind of map, and we have to make sure that that works. Which means that if we go back and see how our code would actually work, which means we have to check, is it any of these types we have seen, because any of these special kinds of arrays have still the same prototype. But we have to check that. I mean, that's already way more complex. And we can go crazy with that, right? This is JavaScript. So I can override the push function if I want. I can say, I can put a property 1 on the array prototype. I don't know why you would do that, but you can, which means that whenever you have an array function, that can actually look that up through the array and get the property there. I can even put the length on the object prototype, which in some cases has weird side effects. Or I can replace the array prototype at all with something completely crazy, the JS proxy in there, which can control everything.
So in short, if you actually want to optimize this array push with a code stub for a fast path, rather than just doing something as we saw with the optimizing compiler, if we don't actually know what's coming in, you need to implement something like this. So you spend lots and lots of time trying to verify that you're actually still in the fast path, and then there's like a pretty slow path at the bottom, which is basically a copy of what the optimizing compiler had But in the end, if you do it this way, you still get a 2x speed up for the slow case, which is a common case in real web pages. And by doing like a set of these optimizations over all the build-ins that, as we prioritize them, we just picked a set of web pages that we could tackle within the time that we had, that we were working on these things, and we prioritized based on those things. And we actually got pretty big speed ups just by speeding up mostly the runtime things that we were focusing on itself. And overall, that gave a pretty nice.
Just if you go back, just to explain the graph a bit, just it's a bit confusing. On the left side, minus is the speed up. On the right side is certain things that we actually slowed down in the course of these two versions that we compared. And parsing and compilation parsing is mostly to the new added ES6 features that blew up our parser by quite a bit, and they're quite complex cases that have to be handled there.
So this is all nice. We improved some things in the real world at least. This kind of brings us back to the question of like, what is a good benchmark? What we built, I wouldn't claim is a good benchmark. It doesn't actually fulfill many of the things that we have. So what it fulfills for us is it gives us priorities and meaningful insights as VM developers. It does give us stable, reproducible things. It doesn't give us a single number. We just have numbers for all the different web pages. We can't actually run it cross-browser at all because we had to hook into the VM to get all these numbers out. But then for application developers and for users, it can actually bring value, because for users, we can look at the real web pages that they are running. So any improvements there have direct impact on the real web. And for application developers, if application developers can send us their applications or could look at these kind of things themselves, given that we're thinking of integrating these kind of things in DevTools, that could give valuable feedback there as well. The other direction. So if you want to look at some of the results that we did get, based on the timings that we have, if you just add up all the times that we spent on all the web pages on the top 25 web pages, these are the results that we have. So the runtime did actually improve. There were some things that regressed a little bit, but overall we get an improvement through the runtime improvements. And within the runtime improvements, runtime is mostly the build-in work. The inline caches, we improved themselves as well, and parse regressed, unfortunately, as Camillo said, due to mostly ES6 work. But if you do want to get a single number out of this thing, we can also still look back at Speedometer that we had originally, which is not what we used to guide our work, but we got a 20% improvement there. So that is it. If anybody has questions. You can also ask questions afterwards.
Yeah.
We'll be hanging around. Okay, thanks.
There's one question over there, quickly.
This looks really great. Any guess on how much better it could get in the future?
How much we can still improve, you mean?
How much more overhead do you think you can shave? Yeah.
I think so. We're focusing on many of these buckets that are in here. Let me go. So you put it way too much back, I guess. Yeah. So we are currently focusing ourselves on the parsing and on the inline cache part and on the runtime part, obviously. So the parsing part especially is a really big part, which we should be able to get should be able to get big improvements out. For a big part, this is also going to be driven by the interpreter work. So that will basically shift around where time is being spent, and that will actually make it easier to optimize things. How much we're going to be able to get in total, that's hard to say, obviously, but we still have high hopes that we can get pretty significant improvements still.
And yeah, what we've seen is we mainly looked at, I think, the 4 websites, there's a Facebook and Twitter that were our main targets for the runtime functions. And if you just look at this graph here, you see that it varies a lot, the usage patterns between the websites. And depending on, if you look at another website, we have actually other runtime functions that we're not really good at or that could be improved. And if we shift a bit the focus on the website we look at, we can gain quite a substantial, get a substantial performance boost on these websites. But it's highly specific to one website. So overall, I mean, on Speedometer we got 20%, but even our top 25, that boiled down to what, I don't know, 3%, 4%. And the more you increase this list, you get sub-fractions of percents.
It all depends what you're looking at, right? We're just trying to prioritize our work mostly, and for specific workloads we can get really big improvements, and for like the overall average indeed you don't get that much. But we do see systemic problems in there, like the parsing problem, for example. Callback is one thing that we haven't really looked into that deeply yet, because it like crosses the boundary into Blink, and if we can make this boundary much tighter, we can probably get quite some out there as well. Callbacks is basically whenever Blink does work, so whenever we leave JavaScript work to do something on the other side, like set a timeout or like do anything that needs to.
Or currently get properties from a DOM node,
yeah, sure.
which jumps back into Blink.
You also mentioned that supporting more of ES6 made the parser slower by a significant amount, even though the sites presumably don't actually use those features, right?
Yeah, exactly.
And that's because you needed more abstraction layers, just in case they might have had those features?
So especially arrow functions, I know is one of the so I haven't actually done much of this work, but I know that arrow functions, for example, made parsing much more complicated for us, because now all of a sudden we don't actually know anymore. Like when you see parentheses, that used to just be an expression list. Now this could be an argument list of an arrow function, and you need to actually keep track of where you're going. So that's just much more complicated to do, like even if you're not in that particular path. Destructuring, yeah, right. Yes.
What is that?
You can have destructuring is a ES6 feature where you can basically assign to a list of variables. Yeah, and the syntax looks very similar to arrow functions, to function arguments. So you have to do the right thing in the parser. Right?
Okay. I guess we'll leave it at that. If you have any more questions afterwards, please come to us. Thanks.